Good, I'm recording now. So as I was saying, so far the math seems to have been doable for you, not too bad. It will carry on a bit like that. I think it will get a bit harder. There'll be some new things. Probably the quantity will increase as well. I was looking at some A-level maths books over the summer, preparing for this. Here's one I was looking at. I mean, obviously, not all of you have done A-levels. Some of you have done different qualifications before coming here. And each A-level, if you did an A-level, has a different exam board, which sets the syllabus and manages the examination. And then within each one of those, some of you have done further maths, some of you haven't done further maths. And if you've done further maths, then there are different options. So this is a statistics student book, which is an option. So some people studying the OCR further maths would have done this, and some people won't have done this. So there's quite a wide spread of what particular maths you've got into so far. Now, basically, in the course I'm doing, in terms of statistics, this book would cover us nicely. If everyone knew everything that was in there, we would have a great start. And really, that's our objective: is to get to the point where the range of topics in this A-level type of book is understood by the whole class. But also a bit more than that. Reading this book, there's quite a few results which are just presented as this is how you do this, this is how you do that. And what we also do in our module is go into greater depth. So we're more about understanding the methods, understanding the assumptions of the methods, and understanding the proofs, which are the fundamental to them. And that's so that we can work as engineers and we can apply the right method at the right time, and we can adapt a method to suit a particular problem that we have. So just to show you a couple of things. So on Blackboard, you'll have seen the resources that are put on there. And so I'm sharing another screen. I can't move that out of the way. I'll put it down there. For this part of the course, we've got a few different resources. There are the mini lecture videos, which I'll be posting each week. And these are the main ways which we're communicating the content to you. And to accompany them, we've got each week there'll be a PDF of lecture notes like this one here that you can see. And this follows the mini lecture videos by number. Sort of this is mini lecture video 4 and so on. And these notes aren't complete, but they give you a structure to help you make your own notes. And so they provide the sort of bit of background information, the structure, but there are blanks left in them, gaps there. And so that's to help you as a way to making your own notes. You can fill those in as you watch the videos and use that to build up an understanding of the course. And then each week you'll have seen that there are questions posted on Blackboard. And to begin with, at least the first few weeks, you'll find that there are loads of questions, loads and loads of questions, and you don't need to do all of them. The questions are there to give you a resource to practice your understanding of the topics. You know, they're there for you to use as you think you need to get on top of it. And you'll find that the questions get harder. So for each mini lecture topic, there's a batch of questions. And as you go through those questions, they'll typically get a bit harder as you go along. And not always just harder, a bit more subtle, a bit more, you have to be a bit more careful in how you interpret the data or how you apply your method to them, so that you can work at those and get better at your methods accordingly. And then the following week, I will post solutions to those. So for the questions that we're doing, that we've been looking at this week, next Tuesday, I'll post solutions. And that's so that it does prompt you, forces you, hopefully, to put some independent thought in it before you start looking at how to do it. And that's valuable because in an exam or other assessment, that's what your experience will be. So it's about you struggling first and working out a strategy to solve it, or working out how to use the resources available to you to understand a problem. Okay. So those are the main things. So the topics this week were pretty simple. The first topics, and some of the material that we're going to present, I'm going to present over this part of the module will seem simple to you. Some of it you might have seen at GCSE, some of it you'll have seen at A-level. But we're starting at the beginning so that we can build the topic up into the complete whole. And if you are finding it too easy, do the harder questions on the that are provided on Blackboard. And if you can do all of those questions that are harder, then that's great. You've mastered that topic. But sometimes you still might find that you think you know the topic, but when you come to apply it, there are aspects of it that you're not so sure about. So that's a good way of testing whether you really do know it. So the starting point was how to interpret experimental data, but also more fundamentally how to use an experiment to find something out that we want to know, to learn something, to increase our knowledge. And in the lecture notes, we had the example of a metal testing machine, which was stretching a small sample of metal until it failed. And we were using that as a way to try and find out how strong the metal was. And obviously, it's a way of finding out how strong each individual piece of metal is that we've tested. But what we really want to know is actually, well, how strong is the metal going to be in general if we have an amount of it in the future? What's its likely strength going to be in that case? What's it going to be on average? And then what's it going to be in the extremes? And how confident can we be that it will be within certain limits? So that's where we started with. And you start with very simple things, with just some data. But then we saw that we can start to analyze that data very simply in the first case by ordering it, finding a median, finding the quartiles, and then we could find the mean. And then we looked at standard deviations as a way of characterizing what was happening. So I've set up a little quiz, first of all, just to check how well you understand one or two of those things. So this is using the same website that Dr. Abdul did. So if you go here, www.menti.com, and our code is 1417386. You will find 3 options, and this is about interpreting a distribution. So I'm going to show you some distributions, and the question is the mean going to be smaller than the median for that distribution? Is the mean going to be bigger than the median, or would you expect the mean and the median to be about the same? So this is about interpreting a distribution and relating that to these 2 most fundamental parameters that describe that distribution. Some people are jumping ahead and answering already. I've not shown you the distribution yet, so I like your enthusiasm, but you don't know the question. So what I'm going to do is show you the question in a moment. I'm going to reset the quiz. Reset. Okay, quiz is reset, and I'm going to show you the questions in a second. Here we go. So I'm going to share that screen again. Okay, so here's our first distribution. So we've got a parameter x, that's our variable, and we've got rho rel on the y-axis. And if you remember, this is the relative frequency density of our distribution. Now, we don't have units for x in this case, but this parameter here has units of inverse whatever the units of x are. It's a density, and so that means that we've divided each of our numbers by the width of the interval. So the wider the interval, the more the lower it would become for the same number of data points in that interval. And it's relative, which means that we've divided the total number of samples we've got. We've divided the number of samples in each interval by the total number of samples, and that means that if we integrated this function, it would be equal to 1. So the area under this is equal to 1. And with a function that looks like this, how would you expect it to look? And so you vote to say, do you think it would be the median will be larger than the median will be smaller than the mean, or the median will be about the same? There we go. So you can see how you've been guessing so far. Thank you to those who've done it. Still coming in. I can't show both at the same time at the moment. Okay, so most of you are saying that in this case, the mean will be larger than the median. So let's take a look at that. So in this case, the mean and the median are shown by the red and black lines, and they're pretty similar, really. The mean is ever so slightly smaller than the median, but it's an instance where they're very close. Okay, so why are they close? Well, in this case, we've got both an even distribution, and it's a pretty symmetrical distribution. The more symmetrical the distribution, the closer the mean and the median will be together. So I'm going to show you another example. I'm going to first reset the quiz. Okay, I'm going to show you another example. So vote again and see if you think that the mean, where will it be? Will the mean be smaller than or greater than the median, or about the same in this case? Let's have a look at what you think. Okay, great. So lots of answers here. And it's a split, it's pretty split, the opinion. The majority of you think that the mean will be smaller than the median, but some think the mean will be larger than the median. So let's take a look. Most of you thought the mean would be smaller. And no, the mean is larger than the median in this case. So the median is the black line and the mean is the red line. So remember, the median is a case of lining up all the data points in order and finding the one in the middle, and that gives you the median. The mean involves adding them all together, adding all the values together and dividing by the total number. So the median is dominated by where most of the particles, or most of the objects or the things are, most of the data points are. And so there's lots and lots of data down here, and then it becomes more thinly spread out. So the median will tend to be closer to where the majority of the data is. The mean is going to be influenced by any data that's further away. So to illustrate what I mean, make that smaller. So to illustrate what I mean, if you have 5 data points, for example, the mean is going to be the middle one. So 5, 7, 9. So the median is going to be 9. And the value of this one doesn't affect the median at all. And obviously, if you found the mean of these, the value of that will affect the mean. And so the mean will be dragged higher than 9 because we've got one data point which is of a large value. So if you have data which has a tail in it, so In this case, we say this is a tail. So we've got a few data points which are quite a long way arranged from away from the other ones, but they will tend to affect the mean because the mean is a function of the values of all the data points. The median is not a function of the value of all the data points. It just finds the middle of them. So we've got one more example. So we'll reset the quiz. Make it a bit bigger. Okay, so one more example here. Do you think the mean will be larger or smaller than the median? Okay, I'm going to take a look at what you think. Great. So the majority of you think the mean is smaller than the median. And we saw the data. The data had a tail coming down to small values. So these small values of x aren't going to affect the median, but they will be affecting the mean. And so that will be dragging the mean towards them. So I would expect the mean to be smaller than the median in this case. And that's what we get when I calculated it. That's the mean and that's the median. So remember that if you have data that's not symmetrical, so this is a distribution that's not symmetrical. If it's not symmetrical, you might expect the mean and the median not to be the same. And if you have data where you have a tail, then that tail is going to be dragging the mean towards it. So it's a useful ability to, or sort of understanding to have, is to be able to relate these parameters to the shapes of distributions that you can see, and that will help you to understand data and interpret it the right way. Great. Okay, so that's one point I wanted to make in this part of the session. Now, the next one was, already there have been a few questions on the discussion board about this thing called the biased and the non-biased standard deviation. And I think that might be pretty new for most of you. I think it can get a mention in the A-level sometimes, but not normally. So I've got a tray of beans here from my kitchen, and we want to characterize them in some way. It might be a case of measuring the mass of each bean, or measuring the length of each bean, something like that. And what we have is, in this here, we've got a population of beans, with lots of beans, and there are more beans than we can measure in total. And so what we do is we have to take a sample of beans, we take some out and think, okay, well, we want to measure those 5 beans and use that to learn something about the whole population of beans over here. And I think in A-level you probably have talked about sampling and some of the problems of that. Just be aware that when you sample, you have to take care that you're sampling in a non-biased way. Obviously, if you take all of your sample from one bit, then you might not get a representative sample. So there are a few factors that can come with that. I won't go into all of those. We got 5 beans. What can we do with those 5 beans? Well, we can measure the length of each of these beans, and we can find the mean value of that length, and we can find the standard deviation, or the variance of that length for the 5 beans. But we're not that interested in these 5 beans in particular. What we're interested in is what it is for these. So if you take a measurement of 5 beans, if you take the mean of those 5, that mean can be used to estimate the mean of the population. And the more samples you take, the closer that value of mean will get to the mean of the population. However, that doesn't actually work for standard deviation. If you take these 5 beans, if you find the standard deviation of their length, you'll have a value. And if you keep on doing that, if you do it again, take another 5, and then you do it again, you take another 5. You can keep on doing it. You get more and more standard deviations from each of these. But you'll find actually, if you take the mean of the standard deviations, you'd think you got standard deviation 1, standard deviation 2, standard deviation 3. If you keep on doing that and take the mean of those standard deviations, you think you might end up with the standard deviation of the population, but actually you don't. There's an offset between the two. And so we call that a biased standard deviation. It's biased because it tends to slightly underpredict the standard deviation of the actual population. And so we have a mathematical correction or expression, which we call the non-biased standard deviation. And if you calculate the non-biased standard deviation of these 5 beans, and the same for these 5, and the same for these 5, and you keep on doing that, and if you take the mean of all of those standard deviations you've been calculating, then that will tend towards the mean of the population. So it's a slightly better estimate of the population standard deviation. When you have a very large number of data points, it makes less difference. But when we're taking samples of like a small number of samples like that with 5, then it makes a significant difference. So that's why we have it. And how do you know which one you want to use? Well, you have to just think about what are you trying to calculate. If you just have 5 beans and all you want to know is the variance or standard deviation of the size of those 5 beans, then that's it. That's the whole population you're interested in, and you used what we call the biased version, and that's what you want. But if you're using these as a sample of a population, then it's different because you're not actually wanting to know the standard deviation of those 5. You're trying to estimate the standard deviation of all these, and that's when you'd use the non-biased version. Someone says, why is the biased one used in some scenarios? Well, it depends what the scenario is, what the right one to do is. I mean, sometimes people might just use the wrong one. Sometimes there isn't much difference between the two. But for example, you know, if I had 5 children, and you can't see that so well. If I have 5 children, and their ages are 5, 7, 9, 12, and 3, then if I say, well, what's the average age and what's the standard deviation or the variance, then it is the normal amount. It's the xi minus x bar squared summed divided by n, and n is equal to 5. And that's because that's the whole population. There aren't any other children that we're talking about. That would be the variance of the ages of that population. But if I was talking about what's the age of children in a school, and you've just taken 5 children out of that school at random and measured, asked them what their ages are, then they're different things. And so then we're not interested in that. We're interested in the standard deviation of the population here. And so in that case, if you're trying to calculate that, then you'd have to use n minus 1 for the non-biased case. Okay, so hopefully that's a bit clearer to you. And that will just be a useful thing to know through your careers to recognize that difference. All right, I had another exercise I wanted to do next. So I can close that lot, I think. So I think you've been doing this with computational methods, but I wanted to just show you how to do some of these things in Excel, just to make sure that you're aware of that. and then we can see some of these things in that context. So here's my screen in Excel. And I'm just going to make it a bit bigger so you can see it a bit better. Okay, so put that there and scroll to the top. So this is a simple problem, and if you look in past exam papers and so on, you'll find lots of questions which are just taking a simple set of data and asking you to analyze it. Obviously, if you've only got 10 data points, it's easy enough to calculate the parameters with a pen and paper and a calculator. As soon as you start getting into hundreds and thousands of data points, then that stops being practical, and we want to be able to do it on a computer. Also, many or all of the functions that we're talking about can be done automatically on a computer. Excel has many built-in functions, and other software that using MATLAB and so on will have many functions in it or calculate things. And so I appreciate fully that all these, many of these techniques are available in an automated way to you, but you need to be able to understand what the computer is doing so that you can input the data the right way, you can select the right function, you can appreciate what the differences between one way of doing a function and another way are. So it gives you that background so you can avoid making mistakes as you go along. So I need to click on this one. There we go. So just a few simple things. And what I'm going to do I'm just having trouble with my monitor. Just trying to fix it. There we go. I just knocked the wire out of my monitor. Right, I can see everything. So what we're going to do is just talk through how to do some of these things in Excel. And you may be familiar with this, but I think some of you won't be. We did these problems last year with the class in computer clusters, and there are quite a few students who were quite new to Excel and weren't familiar with the detail of how to input equations, how to select the right function, and so on. So this will just help you to have a start. And what I'm going to do for the questions for next week, I'm going to include an Excel question a bit like this, and then this will give you some practice just using these techniques in Excel as well, which are specific to stats. So the first question is find the minimum of our data set using the min function. So to input an equation into Excel, you need to start with the equals sign. And I've just knocked my monitor again. So, well, to be honest, I'm not sure. Oh, there we go. It's back. I'm not sure what you can see, whether it affects what you can see or not, but we're okay now. Okay, so equals min. So Excel has a min function. You can see when you type something in, Excel gives you options. And so it's very helpful. And it will help you to learn about other options that are available and the one that you want to use. But for our case, we just want to use min. That's the simplest of those. And we put in either individual numbers, or you can put in an array like that. So you just select and scroll over the cells which contain the data you want it to look at. Put a closing bracket. So Excel arguments or functions always have the name of the function and then brackets surrounding the objects which it does that function to. And in Excel, it doesn't matter whether the function is written in capitals or lowercase, it treats them both the same. So it's looked at that and it's found that the minimum value is 1, and yes, that's correct. Likewise, we want to do that for the maximum value. So we can do the same thing and we get that. Now, why do we want to do that? Well, we want to find a range. We want to find the basic characteristics. And if you're plotting histograms using Excel, you'll want to be doing this to find what suitable intervals there will be. So the range then, obviously, it's the maximum value minus the minimum value. There we go, 7, easy. Use the count function. So most of the names of functions in Excel are pretty intuitive. So if you know what you want to do, you could start typing in the name of that thing, and it will probably give you an option which is similar to what you want to do. And if not, just do a Google search and you'll find lots of handy tips which will tell you what functions do. So how many data points are there? We've got 10 data points, and that's right, we've got 10 there. I can check if you just select them. Excel has I think at the top it says 10 rows we've selected, so yeah, that's 10 data points. Find the sum of the data values using the sum function. Okay, that's easy. So we type in sum, and we then select our range. You see for sum there are lots of different options for sum. You can do some very handy logical operators on what you actually add. But this basic one of sum will add everything that we put in the brackets, and we get 52. And so now we can calculate the mean of our data, because that's the sum of the data points divided by the number of data points, and we get 5.2. So that's all good. We found the mean in a manual way by finding the sum and the number, and Excel will find the mean for you automatically. It has the less intuitive function average for that. Average, you select the data that you're looking at, press enter, and you get the same value. So that's good. So we're checking that we get the same values when we do it our way and when we check Excel's function to do it. So calculate the sum of all, so calculate x minus x bar squared for each data value in column B. So here's column B. So we just want to practice that we can do that. Okay, so equals to start our equation. And we want to square the whole thing. We want to square x minus x bar. So we need to use brackets to make sure we apply the squaring to everything. A2 is our value of x. And then x bar, well, we've got a value for our mean over here, cell F8. And so we can then close that bracket. To do to the power 2 in Excel, raising something to a power, we use this little accent key, which is like a superscript, and put in 2. So that's great. So we do that once and it works. But if you then copy this, so to copy a cell, you can either do, or you can either right click on it and select copy, and then put a new, click on the new cell, and then right click and select paste. It has many paste options, but the first one. Okay, so we've done that. Oh, it doesn't work. Why is that? Let's check what we're looking at. Well, now, by clicking on the equation, it highlights the cells that are being used as arguments in that equation. A3, that's the right one, that's X. But now F9 has moved. That's now, what was F8 has now moved to F9. So when you copy a cell, the references move as well. They move relatively to how you've, to where you've copied it. So that's useful because as we copy it down here, then the value of X will follow the one we want. But it's not useful because we want to stick with our value of 5.2 here. We don't want it to move. So we need to make a correction to our equation. We use the shortcut F4, and F4 puts dollar signs before the F and before the 8. And the dollar sign means that that's then fixed. If we move that cell, or if we copy that cell and paste it somewhere else, the cell reference is fixed. It doesn't move. And if you notice, you keep on pressing F8, it scrolls through different options. You don't have to fix just both of them. You can fix just the row 8 or column F, or neither of them. But we want both of them fixed. So now we fix them. When we copy it, that will follow. Another way of copying, which is often faster, is just to grab the corner of this cell, the little square in the corner, grab it and drag it along. And if you drag it, it will then copy that cell to all the new ones. And now when we check it, you can see that it's kept our fixed value there, which is great. So we've got the individual values of x minus x bar squared. Okay, we've done that. Calculate the sum of all of those. So obviously what we're trying to do here is calculate the variance and standard deviation. So we sum them all up and we get that. it says calculate the non-biased standard deviation. Okay, so we've summed all of these values. What do we need to do? We need to, well, if we're finding the variance, we would first of all divide by n minus 1. So n is the count, that one there, minus 1. And that would be the variance, but we want to find the standard deviation. So then we need to take the square root of that. So the square root is the power 0.5, and we get that. So again, we've done it manually in that case. Is there an Excel function that returns the non-biased standard deviation automatically? Okay, so let's try putting in standard deviation, some stuff here, stdev. That looks like a standard deviation, and it is. But we've got two options here in particular, stdev.p, stdev.s, and they behave differently. So if we pick one of them, stdev.p, it says it's the standard deviation based on an entire population as the arguments. stdev.s is a standard deviation based on a sample as the arguments. Okay, well, what we've got here, let's say this is a sample, so we want to analyze it as if it's a sample. So we pick that one, stdev.s, and then we put in our values. And great, we've got the same answer. So we've picked the right function. We weren't sure, but we've calculated it manually, so we can tell that it is. So stdev.s, so S is standing for sample. And so because this is a sample from a population, and what we want to find is the standard deviation of the population, this is giving us the non-biased standard deviation. And then we can see straight away the version which is going to give us the biased one is stdev.p. So we can select that one and do that. And that's a slightly lower standard deviation. Okay. Excel gives all of its answers by default to many, many significant figures. And of course, not all of those are going to be relevant. We're going to talk about that more in the future mini lectures. Can we adjust the formatting of answer 10 just to show 3 significant figures? So it's an important thing. And as you submit coursework using Excel, just because it's an Excel and just because Excel has a default of showing you loads of significant figures doesn't mean that that's the right number of significant figures to show. And so if you're using Excel to submit work, then you should be presenting your work just as you would with pen and paper, presenting it with a suitable number of significant figures. So you can right-click on a cell, go to Format Cell, and that will give you options as to how it shows that number. Here we go. So if you go to Number, you can pick different ways of doing it. So the only way that you can actually specify the number of significant figures is by using scientific notation, and then that will always show a number as 1 point something or 2.3 times 10 to the something. So by choosing the number of decimal places, you control the number of significant figures. So here we have 2 decimal places, and so that would be 3 significant figures. So that's one way of doing it. That's a bit less convenient to look at sometimes. So you can also just select number, and this means you can control the number of decimal places like that. But it's not the number of significant figures. It will always show 2 decimal places. So you've got a couple of options that can help you to present your data the way that you want. Okay, so now we want to sort the data. We want to find the median. All right, so I'm going to copy the data. So I do Control-C, Control-V to copy the data. And I want to sort it. So if I go to the data icon on the ribbon, you'll see a sort option here. So we can click on sort. Do I want to expand the selection? No, I've got what I want. So I'm going to sort column C from smallest to largest. My column doesn't have a header. I'm starting with the data straight away. There we go. So it sorted the data for me. So that's convenient. What's the median value? So we've got 10 data points in total. So the median will be the one that lies between the 5th and the 6th in this case. So that's our 5th, that's our 6th. So in between those two will be 5.5. So that's doing it manually. Let's just check that Excel agrees. Does it have a median function? Looks like it. So we'll use that one. It says median, and I'll put in our data. And yeah, great, we've got the same. So the median function is giving us the same median. What's the lower quartile? Okay, so if we do it manually, the way that we talked about it in the lectures was to say, okay, well, to find the quartile, what we're going to do is we're going to split the data in half. So that's half our data. And then we take the median of that half to be the lower quartile. So that's 4 would be the lower quartile by that method. And then same for the other half, take half the data and the median of that would be 7. So that's what method we get there. Does Excel have a way of doing it? If you type in quart, you'll see quartile. It's got a couple of options, quartile.exe or quartile.inc. That stands for exclusive or inclusive. If we pick one of those and we put in our data, you have to tell it which quartile you're looking for. So we're looking at the first quartile for the lower quartile. And we do that, and we see that now actually it gives us a different value. Okay, so that's different from what we found. Was it to do with the EXC option? Right, would I try it for inc? And no, well, it's different again. So you remember from the lectures I mentioned that finding the median is, or finding a quartile, there's not a single defined way of doing that. If we showed that on Wikipedia, you'll see a list where people have shown different algorithms that are used in different places on different calculators or different software. And you can see an example here. This is how method 1 in Wikipedia suggested doing it, and this is how Excel's doing it. So there's some ambiguity about which is the at which point is the 25% of the data less than the value, and you can see the effect of that there. So it's an instance of where you need to be aware that software and you might have a different definition. Interquartile range, so that's 7 divided by 4, the upper minus lower quartile. And outliers, so that's, we said if a data point is more than 1.5 times the IQR from the lower quartile, then it would be an outlier. So the lower quartile is 4. So we're going to put in 4 minus 1.5 times the interquartile range. And that would be minus 0.5. And the same here, upper quartile is 7 plus 1.5 times the interquartile range comes to 11.5. So is there any of our data outside of those bounds? No, it's not. So we don't have any outliers on that basis. Okay, so that was a little example to work through to show how these basic parameters that we know mathematically, how they can be implemented in Excel. Likewise, you can do it in MATLAB and other software. We've seen that sometimes there's ambiguity about what method to use, like we saw with the median or the quartile calculations. And so it demonstrates how having your own understanding of what these definitions mean helps you to make your software work the way that you want it to. Okay, so we finished that bit. Just checking in on the chat, where is this going to be uploaded? I'm going to upload these videos on the same, in the week, this week's folder on Blackboard, and you'll see it at the bottom of the videos in there. How are we doing for time? It's almost 2. There was one more little thing I wanted to just talk about before we finish, and that was the other topic, which is propagation of errors. And that's probably is a new topic to all of you, and it's a useful technique. You can use it in labs and so on. And what we're saying is, what do we do about errors in experiments? We're going to learn more about some errors and some confidences and so on in the future lectures. But this is a really useful starting point. So you've got 2 things here. If we measure the length of each of them, use a ruler, measure the length. How accurately can we do that? Well, it's not that great. You'd say maybe plus or minus 1 millimeter for each of those, not meters, millimeters, for each of those measurements. So this is an estimate of the accuracy. It's not as sophisticated as saying it's a standard deviation of the likelihood of what B actually is, because we can't do that. We're just measuring it with a ruler. So this is an estimate of the accuracy. But what happens if we want to do something with A and B, and we want to know how accurate our outcome is likely to be? So for example, if we simply wanted to add the two lengths together, how accurate is that calculation going to be? So let's say that A was 5 plus or minus 1 millimeter. Let's say that B was 7 plus or minus 1 millimeter. What would you do in that situation? Well, one thing you could do is just think, well, what's the worst case? The worst case is that A is, the extremes are that A could be 4 millimeters, B could be 6 millimeters, and then that would give us 10. Or the other extreme is that A could be 6, B could be 8, and that would give us 12. So you can see there that our answer would be, on average, it would be 5 plus 7 is 13. What have I done wrong? 14. Our expectation is that it would be 12 millimeters plus or minus 2 millimeters. So that's one way of looking at it, but that would be the worst case. That's the worst case here and the worst case here, followed, put through together to give the worst case here. And if you consider, well, if these measurement inaccuracies, if they are random and if they are independent of each other, then you wouldn't really expect to get the worst case both times. You'd expect to get a bit of one and a bit of the other, but sometimes this one might be a bit too big, sometimes this one might be a bit too small, and then they would cancel each other out a little bit. So it's not really appropriate. This is a very pessimistic estimate of what the error in our calculation is going to be. And in the lectures, we considered this way of thinking about it, where if you have your error in A and your error in B, this is the worst case scenario for what your error in C is, where they're added together. And you'd say that these are errors which are in phase because they're operating the same way. If they were out of phase, you could have your delta A, but then your delta B would act against that. And so your delta C would be like that. But on average, there would be 90 degrees out of phase. And so you can use quadrature to find what the error, the uncertainty in C is going to be, like this. So that was a sort of hand-wavy argument to suggest that this is a way of doing it. And it seems reasonable in the sense that, you know, this is the case where the errors are adding together. This is the case where the errors are cancelling each other out, and it's likely to be, on average, it's likely to be somewhere in between that, so long as we have independent errors which are random. And then we saw that actually we can prove that vigorously, and we came up with this equation to tell us what the uncertainty in a calculated variable is. So that's the uncertainty squared is equal to the sum of the partial differential of our function with respect to xi times the error associated with xi squared. And this can be a function of many different variables. It can be, in the last one had a function of a and b, but this is true for any number of variables that you want. It's a partial differential. So you just do it for all the different variables that make up f and add them all up, and it will give you a way of calculating the overall uncertainty. So for a quick example, if we said our function was going to be 2 times a plus b, so we've measured our beans and that's what we want to find. Sorry, that wasn't the function I was meaning to write. If it's a squared plus ab, then we can see what the propagated error is going to be. We know the uncertainty in A and B is both plus or minus 1 millimeter. How accurate is our calculation for F going to be? So you do dF by dA. Well, that's going to be equal to 2A plus B. dF by dB is going to be equal to A. And so our uncertainty squared is equal to 2A plus B times the uncertainty in A squared plus A squared times the uncertainty in B squared. And so that gives a nice elegant method for finding the uncertainty in a calculated value based on known uncertainties of individual measurements. Okay, so I'm going to stop there. That's a summary of some of the key points from the mini lectures, and then it also shows how to implement them in Excel. So hopefully you have got a nice grasp of the main questions. Okay, so a few questions on the chat. Let me just respond to those. Do we have a session with the GTAs? Yes, that's going to start straight away when I finish talking. Shouldn't the uncertainty be plus or minus half a millimeter? Well, it could be. It's up to you how well you can read your ruler. I was just saying, for example, that if the accuracy with which you could read your ruler was plus or minus 1 millimeter, yeah, fair enough. Maybe it's plus or minus half a millimeter. Whatever it is, in any particular instance, you decide how accurate you're doing something, you're measuring something, and then that's the error that can be propagated. So, yeah, fair enough. There is two uncertainties, though. So one where you start measurement and one where you need, so we double 0.5, I believe. Yeah, I'm not going to dwell on that. You know what we're talking about. You have a line, you're trying to measure it, and you know, in this case, it's 26 point something millimeters. So if I said it was 26, it's probably somewhere between 26 to 27. I suppose you might say I could estimate, is it closer to 27 than 26? It's somewhere around that in accuracy. Plus or minus 1 millimeter would be a conservative estimate of what that measurement is. Okay, thank you very much. I'm going to wrap this one up and then hand you over to the GTAs. So join the groups that you've been using before, and they'll be ready and waiting for you. Okay, thanks very much.